So we're going to start our evaluation of calculus and physics by looking at displacement, velocity, and acceleration graphs and how they relate. So if we start with just some sort of simple displacement graph, a line moving upwards to the right, this means that you're moving somehow in the positive x direction. If we look at the slope of this, we know that velocity is defined as the change in displacement over the change in time, which is this, the change in displacement, over this, the change in time, which is also the rise over the run. So if I look at this rise over run, I can then plot it down here. So my velocity at this point is a certain slope. At this point is the same slope. At this point is the same slope. Here is the same slope again. Here is the same slope again. In other words, I have a constant velocity. Constantly increasing displacement, constant velocity. So I've taken the slope here and graphed it here. Again, velocity to acceleration. I have exactly the same relationship because acceleration is change in velocity over change in time, which on this graph is, again, the rise over the run. The rise being the vertical part, the change in velocity, the run being the change in time, the horizontal part. In this case, I have absolutely zero change in velocity the entire time, so the graph of my acceleration would be a straight line at 0. Now I'm going to do the same thing, only I'm going the other way. Let's say I start with an acceleration, and let's just start with an acceleration of 0 like I had over here. What this means in real life, of course, is that the acceleration is not going to be there, meaning the velocity is going to be the same the entire time. So let's pick some velocity. Let's say it's this. Notice that this graph with 0 acceleration could be a whole bunch of other velocities as well. It could, for example, be a velocity down here, or here, or here, or here, or here. I've just arbitrarily chosen one at this particular velocity, which we can call 3 meters per second, 2 meters per second, or even just v0. Notice that the opposite of a equals delta v over delta t is the change in velocity equals a times the change in time. Same going from the velocity to displacement, the change in displacement equals velocity times the change in time. That's like saying if I drive at 60 miles per hour north for 1 hour, I go 60 miles. So going from this graph up to the displacement graph, I can figure out what my total change in displacement is by taking a little chunk of rectangle out of this velocity graph. This rectangle on the horizontal side is change in t. On the vertical side is whatever that velocity is, meaning that this times this, or the area of this rectangle, is v delta t, which we've just seen is the change in displacement. So from this point to this point, up here, I have some sort of change in displacement, which means I've gone from this point to another. Notice again that I could draw that particular change in displacement starting almost anywhere, here, 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 or here. I've just arbitrarily chosen to start. If I take the next chunk, let's say the next second, it's the same amount of area, so I go up and increase by the same amount. Same area, increase by the same amount. Same area, increased by the same amount. And as you can see, we have on both sides the same set of graphs. Only this one we started with acceleration and went up to displacement. And this one we started with displacement and went down to acceleration. With one key difference. And that is that here, going from acceleration to velocity, I arbitrarily chose what velocity it was, but I could have had the graph in many different places. And again, going from here up to the displacement, from velocity to displacement, I again arbitrarily chose my starting point. If I have a curved line right here, I have problems. And this is exactly the problem that Newton faced and the reason why he tried to invent calculus. Looking at this curved line, I don't know exactly what the slope is at each point. It's complicated. So what I do instead is I say, okay, if I were to look at a stretch of this, say from here to here, that line right there has a slope, and I can shrink it down to a point here, to a point here, until eventually I have 2 points so close together that they're practically on top of each other, and the final slope I have is the slope of the tangent line of that curve. That's what I'm trying to find. In physics sense, instead of saying delta x over delta t, where delta t is some actual measurable time, what we're doing is we're finding the instantaneous velocity. The instantaneous velocity here we write now as dx dt because it's a little time. Right here we have a big D, it's a big delta, it's a big time, it's a time we can actually measure, shrink it down to nothing, and we get little d t. Little dx because it's a very tiny x, little dt because it's a very tiny t, but it's still the slope. It's the slope at that tangent right there. Now, as it turns out, with this particular graph I drew, if this is based on the equation x of t equals t squared, where t is a variable and x is my function, in other words, the function of how far have I gone in a certain amount of time, and t defines how many meters that is, in this case. If this is the function that I've drawn here, then the velocity with respect to time function will actually be a straight line going up and to the right. That is to say that as time progresses along here, the slope of this curve increases at a very steady rate. In fact, v of t will equal, in this case, 2t. And we'll get into the algebra in a moment. Looking now at the acceleration, as you can see, I have a steady increase in acceleration, so I have some sort of steady positive acceleration, and I can say the acceleration due to t is equal to some constant, in this case 2. Now let's draw the same graphs going the other way again. If I have some steady acceleration, I can determine the velocity again by taking the area at certain integrals, at certain distances. So for example, this area results in a change in velocity of this much, this area of this much, this area of this much, this area of this much again. And I got to say a straight line going up and to the right. But again, I have to arbitrarily choose where I start because I could have chosen down here, I could have chosen here, 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 any one of these places, but I'm choosing this one because, well, it's going to match up over here. Now I have an issue. I can take these triangles and I get sort of this constantly increasing area under here to determine my delta x. Again, thinking that delta x is going to equal velocity times delta t. It does get a little bit more complicated, especially as we have curves, and we'll get into that in a moment. And then up here, I can choose any sort of starting place, and I get this exponential function again. If I take this area, notice that how far I've gone gets bigger and bigger and bigger and bigger and bigger and bigger, not just in how far I go, but in how fast I'm getting there because my velocity is constantly increasing over this time. This is the basic concept of calculus. Either taking what's called a derivative, finding the slope of the line and slope of the line and slope of the line, or taking what is called the integral, finding the area under the curve or the area under the curve or the area under the curve going the opposite direction. And they are, as it turns out, opposite functions of the same basic concept. Now I want to take a closer look at what's happening with the integration when I'm finding the area underneath this particular function. For example, what if my acceleration were a bit more complicated? Some sort of a curve, something that's not just simple rectangles or rectangles and triangles. What do I do now? How do I figure out what the area is, what my change in velocity is? Well, one way to approximate it is to come in and make little rectangles at certain spots. So here I've made some rectangles, and notice there's a little bit of extra there, but it's sort of a close estimate. And if I want to get even closer, I can make even smaller rectangles. So if I have smaller rectangles, notice that the gap between my rectangles and the actual area under this curve gets smaller because I made smaller rectangles. Well, what if I kept shrinking the rectangles until they're super tiny? In fact, what if I had an infinite number of them, infinitesimally small? So if I have an infinite number of rectangles, infinitesimally small, then eventually I would have no gap left here between the curve and my rectangles, and I would know exactly what the area is under there. Well, that's what we call integration. So we could write this as the sum of all those little rectangles. The bottom part of the rectangle is going to be delta t wide. This vertical part is going to be the acceleration. So the sum of the acceleration times all these tiny ones, except again, it's no longer the delta t. We have a sum of acceleration delta t, but when we shrink it and make it infinite, we write this nice little sign, another sort of an s, a dt, using dt now because we've shrunken these to these tiny, tiny little rectangles. Little tiny rectangle times the area gives us some particular area underneath that curve. This is how we write it. This is how we do integration. Integration is just finding the area under the curve. It gets complicated with more complicated curves, but that idea, the basic idea of all of this, is just finding the area under the curve so that we know, for example, here, what that particular change in velocity is. Woo. One thing we need to pay close attention to is as we're going up here, if I take the integral of a dt, let's say it's equal to, one thing we need to pay particularly close attention as we move from the other one to the other is remember that we could start almost anywhere up here. So whatever the result is of this function on A, we need to make sure that constant being whatever we start with. It could be totally arbitrary, it could be something you get to decide, or it could be within the parameters of the problem. They might say, oh, well, your initial velocity has to be 3, and then you have to add 3 onto your integral. So if I say a dt, if I say the result of this is, for example, at, it's not just at, it's at plus that initial constant v0, v0. If it's 0, then it's 0. If it's -3, it's -3. If it's 3, it's 3. Let's look at the most important derivatives for introductory physics. Let's say I have something called x of t equals t squared. That's the equation we looked at before. What then is my derivative of this? I would write the derivative, again, dx of t dt. In other words, the change in x, infinitesimally small, divided by the change in time at an infinitesimally small point. dxt dt. This is how I write the derivative. And in this case, it's going to be equal to 2t. X of t equals, say, t cubed. Then d of x of t dt equals 3t squared. Now, there are a couple problems. One is I don't like writing dx of t over dt all the time. A lot of physicists don't. So we have ways of abbreviating it. I'm going to show you the way of abbreviating that I like to use. And that is to say, instead of dx of t over dt, I'll just write x prime t. X prime t means first derivative of this function x on t. So x prime t of this is 2t. Now let's look at several different functions. If x of t is t squared, x prime of t is 2t. And here's the basic rule we're going to use for simple functions like this. If it's t squared, then I take the 2, I move it down here, and I subtract 1, and I get 2t. If it's t cubed, I take the 3, I move the 3 down here, I subtract 1, and I get 3t squared. T to the 4th, subtract 1, move the 4 down here, and I get 4t cubed. T to the 5th, move the 5 down here, subtract 1, and I get 5t to the 4th. In fact, for any sort of t to the n, I take the n, move it down there, subtract 1, and I get n t to the n minus 1 as the first derivative. We also have what's called the second derivative. In this case, with a function of displacement, this would be the acceleration, whereas the first derivative is the velocity, the second is then the acceleration. So x2 prime of t would then be, take this down, n minus 1 times n times t to the n minus 2. As an example, if I have t cubed, the first derivative of the velocity is 3t squared. The second derivative is then going to be 6t. If I start with some sort of constant, like say 3 in front of my variable, that's fine, the constant just stays there. So then I get 2 times 3t, or 6t. If I only have exponent of 1, then I get 6 times t to the 1 minus 1, which is 0, which is 1, so I just get 6, the constant. Another important factor here in the derivatives is that I have any sort of addition, say 3t squared minus t cubed plus 5. Each one of these can be taken as separate derivatives, and it works out just fine. So I get 6t for the first one, 2 times 3, and t to the 2 minus 1, minus 3t squared. And then I have plus 5. Well, I don't have any t here whatsoever. Any sort of constant that is not does not times t, which is the variable under which I'm deriving this, just goes away. I don't have to worry about it anymore. So this would be 6t minus 3t squared. If I take the next derivative, I get 6 minus 6t. What if I have to go the other way? I know my acceleration with respect to time, which of course we said was the second derivative with respect to time. Let's say that's equal to some constant, 6. What then would be my velocity with respect to time? In other words, the first derivative. Well, the really cool thing about this relationship between integrals and derivatives is that this is simply whatever it needs to be in order such that when it is differentiated, it becomes 6. And that number here would be 6t. Notice that we differentiate from 6t, we get t becomes just 1, and we're left with 6, the constant. But we're not quite done, because it's 6t plus some constant. In this case, we usually write the initial velocity, since we are talking about the velocity. What are the initial conditions of the velocity? So 6t plus v0. And in the same case, if I look at the displacement, x of t, what does x of t have to be such that the derivative, the first derivative, gives me this x prime of t, the velocity? Well, I'm just going to make a guess here. Let's say I try 3t squared. Notice that 3t squared, if I derive this, I would then get 2 times 3, or 6, and then just t. So this indeed will become 6t. But I have this other constant plus VO, which is a constant times t. So in order to get the VO, I need VOT, plus whatever constant I need for my displacement, XO. More often than not in physics, we're going to be dealing with some sort of definite integral. So let's say that I know the acceleration is defined as this. Acceleration is equal to 6t. It's been defined in this, where t is in seconds and the acceleration is in meters per second squared. And let's say I want to know, for example, what is my change in velocity between, let's say, from 2 seconds to 5 seconds. This is what it would look like in terms of an integral. I would say I am integrating from 2 to 5 on this function, 6t, that's my acceleration, dt. Let's go back to the graph and see what that looks like on a graph. And the acceleration at the time, here's my 2 seconds, here's my 5 seconds. And here I have some sort of function, 6t, which is going to move up and to the right like that. That's my acceleration, right there. So I'm saying I don't want to know what my total change in velocity is from 0 out to 5. I want to know this. What is the area of this triangle right here? Naturally, it's a fairly simple function, so I just have a straight line. For a more complex function, I'd go about it the same way as I'm about to show you here. So first, let me integrate this. The 6t would then have to be, well, 6t squared, but 6t squared would bring me to 12t, so it's 6 over 2t squared. In other words, 3. So my answer is 3t squared plus some constant, let's call it v0. And generally in calculus we write like this. If we have not yet resolved the area just between these two sections, we can write it intermediary with sort of this little bracket here and a 2 and a 5. And what this says is I'm taking 3 times 5 squared plus v0, this solution to the function, minus 3 times 2 squared plus v0. And if I work that all out, I get I get 25 here times 3, or 75, minus 3 times 4, or 12. And so I end up with 63. And notice I have plus VO and then minus VO. So I get just 63 meters per second. And that is my change in velocity from 2 seconds to 5 seconds. Notice that my initial velocity, it didn't matter. It didn't matter. And that's because when I graph it up here, my velocity versus time, I have an increasing velocity. It looks like this, or it looks like this, or it looks like this, or it looks like this. But the change between here and here, or here and here, or here and here, my change in velocity is the same for every single one. So if all I'm looking for is a change in velocity between 2 specific times, this constant drops out. In fact, it drops out so much that a lot of people tend to forget to even write it when they're solving a definite integral. So I'm going to show just a brief proof, a brief demonstration of how we actually get those particular relationships. And I'm only going to look at it from the differential side, as how we find it if we're taking a derivative. I'm not going to worry right now about the integral or why there's this particular relationship. You can work on that in calculus class. If I have some sort of graph here, and I have my curve, and I need to find what happens in here first, instead of doing the curve, I can just find the slope of this particular line. Notice that this is t and this is x. This is, right here, some t later. This is some initial t, some t initial. This is some t plus my change in time at some point later. This lower line right here has a value of x of t. The upper part up here has a value of x of t plus delta t. So this side right there has a value of x of t plus delta t. In other words, the value of the function at this point along this horizontal axis minus x of t, the value at that low point there. Similarly, this side here has a value of t plus delta t minus t. And what we're going to do is we're going to say, okay, as this point gets closer, and then closer, and then closer, and then closer, and then closer, we're going to get closer and closer and closer to the actual real slope. In fact, we're going to shrink it down to 0. In other words, as delta t goes to 0, what happens, what sort of value for the slope are we going to get? In this case, we're going to focus on this very simple function, x of t equals t squared. And then I'm going to write out my slope here. My slope is equal to x of t plus delta t minus x of t divided by t plus delta t minus t. And I want to find the limit as delta t goes to 0 of this expression. So I'm going to go ahead and substitute in my actual function is this. So I have the limit as t goes to delta t of t plus delta t squared. That's this first function. Minus the second one, which is simply t squared, divided by t plus delta t minus t. So the limit as delta t goes to 0. If I expand this function, I get t squared plus 2t delta t plus delta t squared minus t squared divided by t plus delta t minus t. And now, quite conveniently, we have several things that cancel out. On the bottom, I have t minus t. And on top, I have t squared minus t squared. So limit as delta t goes to 0 of 2t delta t plus delta t squared divided by delta t. And this on its own isn't doing us much good because as delta t goes to 0, we have no idea what this is doing right now. The delta t we can't divide by 0. But, lucky for us, notice that we have a delta t in this expression, and we have a delta t over here as well. In fact, I can rewrite that as delta t times delta t. And so, I can divide out by this delta t on the bottom, and I end up with the limit as delta t goes to 0 of 2t plus delta t. Easy limit to solve. As this becomes 0, no problem. We're left with just 2t. So that is the limit as delta t goes to 0 of 2t plus delta t. Back to our graph, that means, notice I did this very generally, I didn't put in specific numbers. That means anywhere on here, the slope of this line is exactly equal to 2 times the value on the horizontal axis. So the slope at 1 is going to be 2. The slope at 2 is going to be 4. The slope at 3 is going to be 6. And so on as this parabola goes up towards infinity. And notice this also corresponds to the rule we talked about earlier. The 2 moves down in front, and 2 minus 1 leaves me just 1 as the exponent on the t. And I invite you to try this exact process with any other thing like t cubes, t to the 4th, 6 times t to the 15th, just to see that as you work it out, you end up with the exact same result as predicted by the little rule that I showed you earlier. Good luck.